little bit on Friday when we talked about Earth's magnetic field. We said Earth was a giant electromagnet. We said Earth was a giant electromagnet because it's convecting magma inside the mantle, which is causing charged material to move. That motion of charged material creates creates a magnetic field. So the motion of charge creates magnetic fields. We can demonstrate that very by using what is called a power supply and a compass. So what I've got here is a variable voltage power supply. You guys will be using this later next week. And all it does is it's going to act like a giant battery for me. And I'm going to just connect a couple of wires here. So I'm completing a circuit. Yay, there's nothing on this circuit. So it's very low resistance, meaning I can get a very high current very easily. Next piece of material I'm going to use, a compass. Compass is currently pointing red arrow towards me, so that direction is north. And I'm going to lay this wire on top of it, making sure that I do this correctly. Yeah. So I'm going to just lay the wire on top of it, and I'm going to turn on the system. Turn on the system, and the compass is now pointing the opposite direction. The magnetic field underneath the wire is pointing in that direction. If I turn this off, compass will go back to normal. Okay. Let's say instead I'm going to lay the wire vertically over the top of this thing. Okay. So now it's north is still this way. I turn this on, and my compass is now pointing perpendicular to the wire. Okay. I can also take this compass and go above the wire and show that it points to my left. Okay. Just looking at those few compass readings, what does that tell you about the magnetic field created by current in this wire? It's perpendicular to the wire here and here. Anybody got another way of describing it? So if here, I'm going that way, here, I'm going that way, what's going to happen here and here? Right, it's going to start creating a loop. Okay, so when we have motion of charge, the charge creates a magnetic field in a circle around it. So if, and I've got a couple of symbols here I'm going to want you to learn. So circle with a dot in it means something coming out of the page. And X simply represents something going into the page. So if I've got a wire carrying current here coming out of the page, I can show that my magnetic field is going to be created in a counterclockwise fashion around that wire. I'm going to use the letter B to represent magnetic field. Conversely, if I have a wire carrying current into the page, I'm going to create a magnetic field clockwise around this. Okay. To help you remember what direction the wire actually creates a magnetic field, we use what are called right-hand rules. So the right-hand rule for a current carrying wire, right-hand rule for current carrying wire, shows us that if your thumb points in the direction of current, then your fingers will wrap in the direction that the magnetic field is being created. So in the situation where I've got current coming out of the page, my thumb's pointing in the direction of out of the page, my fingers will now curl in the direction the magnetic field is being created, or in a counterclockwise circle. Yeah. Don't use your left hand. It's the right-hand rule. This should be easier if you're left-handed, because that means you get to write with this hand and figure stuff out with this hand. So it's actually advantageous to be left-handed here. Okay. So right-hand rule for current carrying wire. thumb points in the direction of current. And your fingers wrap in the direction of the magnetic field. Wrap in direction of magnetic field. Okay. Questions on that? So if I have a wire and I want to make a more intense magnetic field, I've got a few options that I can use. First of all, I can increase the current. Well, that's not always a great option because that means things get hot faster. That's a more dangerous scenario. We don't always want to just increase the current. The other thing I can do is I can stack up the wire. I can create a loop. So now I get the magnetic field from both the bottom portion and top portion, and I can just keep going. So for every loop that I stack onto here, I multiplicatively have stronger magnetic field. So three lines is now going to be 3 times as strong of magnetic field being created. Okay? So for this one, if I've got, this is going to be coils and solenoids. If I've got a coil of wire where I have current going this way and looping around once, twice, and then back out. So current's going that way, current's going this way. I can figure out what the magnetic field is created by this coil on the inside and the outside simply by looking at this in segments of wire. So on this segment of wire, on the top here, current's flowing this direction, meaning that magnetic field above the wire comes out of the page, below the wire goes into the page. So out of the page, into the page. I can carry that over to the side here where I have magnetic field, current carrying wire, carrying the current towards the bottom of my page, current going into the page on the inside, out of the page on the outside. So into the page, out of the page. And this trend carries all the way around my coil. Okay. In this case, when we're working with a coil or solenoid, rather than try to use that right-hand rule for a single wire multiple times to figure out which way the magnetic field is being directed, we can actually just use a new right-hand rule, which is literally the inverse of the first one, where our fingers are now going to follow the direction that current wraps around the coil, and your thumb will then point in the direction of the end magnetic pole. So you'll notice here my fingers are curling in a clockwise direction, as did the current in the coil, and my thumb is now pointing into the page in the direction of the end magnetic pole. So right-hand rule for coils. For coils is your fingers wrap in the direction of current. Fingers wrap in the direction of current. And your thumb points in the direction of the end magnetic pole. Thumb points in the direction of end pole. Okay? So we can actually use this to create much larger electromagnets. So what I have here is a solenoid. A solenoid is simply a piece of metal with wire wrapped around it. And I can, depending on how I connect my power supply, I can make a electromagnet with the end pole on either end of this. So first of all, I'm going to connect my positive lead to this end so that current's going to wrap in this direction. When it does that, this is now going to be my end pole for this electromagnet. When this is my end pole, my compass's white end will point towards it because the white portion is the S pole. right? Connecting that here, connecting this here. Again, using my right-hand rule for a solenoid, the wire is wrapping in this direction. This is now an N pole. Turn on my power supply, and almost immediately that flips to upside down. Good? Now, I do have a little bit of a permanent magnetic field in this nail. So what I'm going to do is I'm going to reverse the leads, because you'll notice it's still magnetized, it's still attracted, but I want to show you that it's an electromagnetic field that's being created, not just the permanent magnetic field of the nail that matters. So I've flipped the leads, and the line now goes, let's see here, in this direction. So this actually is knotted up here. I'm following this by following the curve out of my coil here. So this is my S pole. Turn that on. Allow this to actually spin. Did I mix this up? Oh, whoa. Okay, so I've got my N pole there, or sorry, my S pole there, and my N pole here. All right. Questions about the solenoid piece? Okay. I'm going to draw this one more time. This is kind of a top-down view. What I'm really doing is creating a iron core. We have the nail in this case, not because it's necessary, but because it strengthens the magnetic field that would be created by the electromagnet. So without the iron core, I can still get a magnetic field to be created. But by placing a whole bunch of iron domains in the middle, it gets way stronger. I've got a wire, comes this way, wraps around, loops here, comes out this side, and if I connect it to a voltage source, where this is the positive end, this is the negative end, wraps in this direction, this becomes my N pole, this becomes my S pole, following the coils like that. And I now create a magnetic field that looks like this. And you should kind of recognize this drawing. Say again? Where have you seen something like this drawing before? Not that far back. Yeah, the permanent magnets we drew on Friday. Or Earth. Yeah, Earth would work as well. So we drew basically the same form. The magnetic field created by an electromagnet is the same as a magnetic field created by a permanent magnet. The only difference is I can turn off an electromagnet. I can't turn off a permanent magnet. I mean, unless I, hit it violently. All right. Questions pertaining to solenoids or this right-hand rule concept yet? No? All right. So next up is force on an electric charge, magnetic force on an electric charge. Magnetic force on an electric charge. All right. So we've clearly established that moving charges create magnetic fields. Yes? That means that a moving charge should interact with a pre-existing magnetic field. Because if your moving charge creates a magnetic field and magnetic fields interact with each other, we already knew that from Friday, opposites attract like fields repel. We can determine the direction of force acting on a moving charged particle using yet another right-hand rule. So right-hand rule for moving charge. In this case, our fingers represent the direction of a magnetic field. Fingers represent direction of existing magnetic field. of existing magnetic field. Your thumb points in the direction of positive charge motion. In direction of positive charge motion. And lastly, when you align these two parts of your hand like this, your palm will be facing the direction of the applied force on the charge. Yep. Points in direction of force on the charge. Okay. All right, so drawing out an example for this. If I've got a magnetic field, I'm going to label that B, pointing to the right, and I have some positive charge moving through the field. I'm just going to write Q positive. My fingers point in the direction of the magnetic field. My thumb points in the direction of the moving charge, and therefore my palm is now facing the direction that the force would be felt on this object, which would be into the page, or down in this case. So force is into the page. Okay. With this, I want to point out that the charge, the field that it's moving through, and the force are always all mutually perpendicular. If the charge is not moving perpendicularly through the magnetic field, no force is felt. Force is only exerted if velocity and magnetic field are perpendicular. Okay. And we can quantify this force as F is equal to QVB, where F is force, Q is the magnitude of the charge, V is the velocity at which it is moving, and B is the strength of that magnetic field.